In this video, we will explore the concepts of ROC and AUC, essential tools for evaluating binary classification models. The ROC curve, or Receiver Operating Characteristic Curve, is a graphical representation of a binary classifier's performance. It plots the true positive rate against the false positive rate as the decision threshold changes. This is a typical ROC curve. The x-axis represents the false positive rate, while the y-axis represents the true positive rate. The orange arrow indicates the direction of increasing thresholds. The true positive rate, or TPR, is calculated as the ratio of true positives to the sum of true positives and false negatives. Similarly, the false positive rate, or FPR, is calculated as the ratio of false positives to the sum of false positives and true negatives. Notice how true positives and false positives play key roles in calculating these metrics. The ROC curve plots TPR versus FPR at various thresholds. An ideal model's curve leans towards the top left corner, while a curve close to the diagonal line represents random guessing. In this scene, we will thoroughly explain and visualize AUC, or area under the curve. AUC is a performance metric for classification models. It measures the area under the ROC curve, which plots the trade-off between the true positive rate and the false positive rate, the x-axis. Labeled false positive rate, represents the proportion of negative samples incorrectly classified as positive. The y-axis, labeled true positive rate, represents the proportion of positive samples correctly classified. The perfect classifier achieves an AUC of 1. Its curve touches the top left corner, indicating no false positives and perfect true positives, indicating ideal performance. Random guessing has an AUC of 0.5, represented by the diagonal line. It shows no distinction between positive and negative classes. A good model achieves an AUC of 0.9. The curve is closer to the top left corner, showing strong distinction between classes. Here we highlight a specific point where FPR is 0.2 and TPR is 0.96. Now, let's focus on the dynamic visualization of the ROC curve. The x-axis, labeled false positive rate, represents the proportion of negative samples incorrectly classified as positive. On the y-axis, labeled true positive rate, we have the proportion of positive samples correctly classified. First, we construct the graph using axes for our visualization. The ROC curve will be plotted on this graph to illustrate the trade-off between sensitivity and specificity for different thresholds of a classification model. To make our visualization more interactive, let's add a horizontal slider at the top of the ROC curve. This slider represents the threshold, allowing us to dynamically adjust it and observe its effect on the ROC curve. The position of the yellow dot on the slider determines the threshold value, which dynamically updates the ROC visualization. The threshold value is displayed numerically above the slider for clarity. As the threshold slider moves, the orange dot travels along the ROC curve. The shaded region expands, representing the area under the curve or AUC, dynamically updating its value on the screen. Let's first focus on the strengths of ROC and AUC. These metrics are ideal for binary classifiers and excel in scenarios with imbalanced datasets. They also help when the costs of false positives and false negatives differ. Like in medical diagnostics, where misclassifications can have serious consequences. Additionally, ROC and AUC summarize model performance across all thresholds, making them excellent tools for comparing multiple models visually and intuitively. While powerful, ROC and AUC have limitations. For instance, avoid using them with datasets that have extreme class imbalances. Precision recall curves often provide better insights in such cases. Similarly, if you care more about a specific threshold, like a fixed probability cutoff, metrics like accuracy or sensitivity may be more practical. Remember, choosing the right metric depends on your problem's context and priorities. To illustrate, here's a side-by-side comparison of ROC and precision recall curves for an imbalanced dataset. Notice how precision recall provides clearer insights when positive samples are rare. On the left, we have the ROC curve, which plots the true positive rate against the false positive rate. This is commonly used to evaluate binary classifiers. On the right, we see the precision recall curve, which is particularly effective in cases of imbalanced datasets where the positive class is much smaller than the negative class. The ROC curve illustrates how well the model distinguishes between classes across different thresholds. A perfect classifier would pass through the top left corner, achieving a true positive rate of 1 and a false positive rate of 0. The precision recall curve, on the other hand, focuses on the performance of the positive class. Precision measures the proportion of true positives out of all predicted positives, while recall measures the ability to identify all positive samples. Here, we are highlighting specific points on the curves to show how the performance of the model evolves as the threshold changes. On the ROC curve, the model's ability to balance false positives and true positives is emphasized. On a precision recall curve, notice how the balance between precision and recall shifts as the decision threshold varies. Watch as the points move along the curves, providing a dynamic perspective of how thresholds impact the model's performance metrics. As we've seen, while the ROC curve provides a comprehensive overview. In summary, ROC and AUC are excellent tools for evaluating models across thresholds. However, always consider the problem context and choose the metric that best aligns with your specific requirements. That's all for today's video. If you found it helpful, don't forget to give a thumbs up, like, subscribe, comment, and share. Thank you for watching, and see you in the next video.